Hello, I'm Leslie Rusch from the Université Laval in Quebec City in the Center for Optics, Photonics, and Lasers. I'd like to thank the organizers of the workshop today for giving me the opportunity to speak to you, in particular about challenges and opportunities in scaling silicon photonics to higher baud rates. So higher baud rates in access means we have to deal with direct detection. Where can we increase capacity and profitability? Well, clearly higher baud rates are going to allow us to support more clients, but wider bandwidths are only one step. We also have to make sure that we design our integrated devices to really meet the system environment for access. So I'm going to talk about a few opportunities where we can use photonic integration for these means, and that is by using complex signaling and optical signal processing. And so these two things will be directly related to achieving higher baud rates. But I'll also talk to you about a second way of looking at things, and that is to think about higher baud rates meaning higher capacity. And how could we use that capacity? And we can use that capacity perhaps to support heterogeneous services, and in particular I'm going to talk about radio access networks. So if we're going to be designing devices for the specific systems for access, that means we're going to be designing devices which are low in cost, small in size, and with low power consumption. So if I'm looking for these three attributes, it's not going to be surprising to you today that I'm going to be talking about microring modulators as they hit the sweet spot for this. So we'll begin with direct detection. Why complex signaling for direct detection? Well, what we see here is a frequency plot of chromatic dispersion-induced power fading. So this is the channel response for, I think it's an 80-kilometer fiber in this case. And you can see that for even moderate gigahertz bands, we can have significant fading. And this, of course, is for the C-band. And this is what limits the bandwidth and therefore the highest baud rate that can be supported. Certainly in the O-band, we have less chromatic dispersion, but eventually this dispersion does kick in, and it simply does it at greater distances. So where does this chromatic dispersion-induced fading come from? It comes from the use of double sideband modulation. So here I'm showing the power spectral density for a typical double sideband modulation. We have the carrier in the center and two sidebands to either side. So as long as these two sidebands see the same channel, we will not have any fading. However, in a dispersive channel, what we have plotted here on the side is the delay versus the wavelength. And we can see if we focus our attention on the C-band, that if I have these two sidebands on either side of the carrier, that one sideband will see different dispersion than the other sideband. And because of this, we'll get non-coherent combining at the direct detection, which leads directly to the fading. So how do we avoid this? Well, we don't use double sideband modulation. We use single sideband modulation. And this simply avoids the worst of the fading. So this single sideband modulation is compatible with Nyquist PAM in baseband or OFDM in passband. I'll show you now some idea of how this double sideband versus single sideband plays out. So in this case, I think we have a 20-kilometer link with OFDM. And on the left here, I show the electrical spectrum in doing detection of double-sided modulation. And we can see also here is an inset of the QPSK constellation on one of the subcarriers for OFDM. And we can see here that the constellation is completely unrecoverable. There is severe distortion of what should be a flat spectrum due to the presence of chromatic dispersion. Now, here on the right, we've used single sideband modulation. And the way you accomplish single sideband is you can generate you can sculpt the frequency content if you use a complex modulation format to eliminate the lower sideband. So here is after electrical detection, and the single sideband has been detected. So in the electrical domain, now we have two sidebands, but they are not affected by fading. And you can see here that the QPSK constellation is completely recoverable. So how do we achieve the complex signaling? Well, we can use an IQ modulator. And in particular, I'm going to talk about using microring modulators because these are CMOS compatible for lower cost Very compact footprint, 20 micrometers radius for this MRM that you see sketched on the side. They're very power efficient. We're talking about something on the order of milliwatts. And if we put this in a Mach-Zehnder configuration, such as we see here, we have two microring modulators forming the in-phase and the quadrature branches with the pi/2 phase shift between them. So with this setup, we can achieve complex modulation where we drive the I and the Q with separate signals. So we have demonstrated the use of a microring modulator in IQ modulator in silicon photonics for this application, and we achieved 31 gigabits per second QPSK OFDM. And this is the frequency response of the microring modulator that we used as a function of different detunings away from the resonant frequency of the microring modulator. You can see that it can be very wideband indeed with 3 dB bandwidths in excess of 25 gigahertz. So this is very wide band, but another attractive aspect of microring modulators is its compatibility with wavelength division multiplexing. And so here we take that same Mach-Zehnder infrastructure and now we create a bus with several pairs of microring modulators on this bus. So a comb source could be input to this Mach-Zehnder structure. Each one of the microring modulators is modulated with a particular signal for that wavelength. And what we output is a bunch of single sideband modulated signals. So no wavelength multiplexer is required. Of course, if we used a non-frequency selective Mach-Zehnder modulator, a typical one, we would require an array waveguide grating also. So this reduces the count of devices, keeps the power down, also keeps the footprint very small. So we've seen microring modulators for complex modulation, very clear economic advantages. Of course, there are still some issues with using microring modulators. We still have to work with stability, have feedback circuits that allows us to stay on the resonances of these microring modulators, but this is very achievable. So another problem with direct detection is signal-to-signal beating. So I'm going to talk about optical signal processing that will let us deal with this impairment. So even if we use single sideband modulation and fading is avoided, we still have to worry about the signal-to-signal beating. So just to briefly remind you of what SSBI, or signal-signal beat interference, is, this is the electrical spectrum after square law detection for OFDM. So we have the carrier, which becomes a DC component in the electrical domain. The OFDM signal has beat with the optical carrier to create this nice rectangular spectrum. But the OFDM signal in square law detection beats against itself. And this creates what we call SSBI. It has a triangular spectrum here, and it overlaps with the OFDM. So the yellow here, this yellow triangular spectrum, is undesirable. It's interference when I try to detect this desired orange rectangular spectrum. And of course, this brown percentage of that rectangle is interference, which impairs reception. One solution to dealing with SSBI is to simply create increasing guard band. So if I create a guard band, that means that the overlap between the triangular and the rectangular spectrum is getting smaller. And we can see here that the brown part of the orange spectrum is really quite small. But of course, this solution is not very spectral efficient. Another solution would be simply to increase the power of the carrier. So we see here the DC component getting larger because the carrier has gotten larger, but because the OFDM beats with the carrier, as the carrier becomes more powerful, the OFDM signal becomes stronger. And so although the SSBI remains the same, the overlap section becomes much less important percentage of the overall spectrum, and so the interference becomes smaller. Of course, this solution requires us to sacrifice power efficiency because we need a stronger and stronger carrier. There are other methods also to deal with SSBI, such as DSP, but ultimately the DSP solutions are also trading power efficiency. So what can photonic integration give us? We can look at a hardware solution to eliminating this beat interference. So for instance, here we have a signal which comes in with the carrier and the OFDM spectrum, and we simply split it into two versions, and in the upper portion we have both carrier and OFDM, and in the bottom we put in a microring resonator, and the role of this resonator is simply to eliminate this carrier. So here at the output we simply have only the OFDM signal, no carrier. So if I next put this through a photodiode, that means that these photodiodes at the top is going to be showing you the spectrum I discussed earlier, the desired signal plus the interference in the triangular spectrum. But in the lower branch, I will only have the triangular spectrum. And in this case, I can now do a subtraction in the electrical domain so that all the interference is removed. In fact, there's also a way of doing a polarization diverse solution in silicon photonics. So here we would use a polarization splitter rotator in order to treat the various polarization components. So having covered the complex signaling and optical signal processing methods which can lead directly to higher baud rates, now I'd like to talk about how I can also increase capacity and profitability once those higher baud rates have been achieved. And that is via heterogeneous services and radio access networks. And once again, the microwave modulator is going to play an important role. So here I have done a drawing of a typical passive optical network, but next generation network where there are multiple wavelengths. So from the central office, we modulate data onto each of the different wavelengths, multiplex them here, assuming that we needed a multiplexer, an AWG, send it through the feeder network, and at the remote node, we're going to split each of the different wavelengths to service different clients. Now imagine that one of these clients, now that I have added capacity, WDM, I could support different services for just like a 5G base station. So that could be one of my clients. If I want to be a little more avant-garde, I can also think about adding a antenna, not a full-blown base station, but create maybe a picocell for 5G by adding simply an antenna to an existing digital customer. And of course, this would require that this link support both the digital services and a radio over fiber coexisting. So if we take these ideas even farther and we make a richer environment for our passive optical network infrastructure, we can imagine turning this remote edge into what I call a smart edge. So this is very much in the paradigm of 5G deployment, so that different base stations can share information about the various mobile users that they're supporting so they can coordinate at this smart edge and make increases in coverage and in support for these various mobile users. So how do we achieve this migration of a passive optical network to a version with a smart edge? Well, we can use silicon photonics as enablers at many, many steps along here, from the central office to the smart edge to the optical network units at the customer premises. So for instance, if we start with the central office, we could use a laser comb as the input and have a bus structure of the MRMs, IQ MRM modulators. If we look at the smart edge, we could use a modulator to create small comb generators. So we could have a main frequency and create a couple extra comb lines, and those extra comb lines, we could use microwave modulators to add onto them the radio over fiber for transmission to the 5G antennas. At the customer premises, we could also use the add-drop nature of these microwave modulators to separate out the different components, the digital signaling from the radio over fiber, the RF signaling. Each one could be peeled off and dropped. And in fact, we could have a microwave modulator which lets us reuse the carrier in the uplink. So from these ideas, we can support different kinds of services. So in conclusion, I'd just like to acknowledge our industrial partners, and also to remind you that we've seen that access networks are dominated by cost, size, and power, for which microring resonators are very appropriate. And we've looked at both OFDM for high rate signaling and also RF transport for heterogeneous services. Thank you for your attention.